Hello everyone. I want to go over the exercise that we did in class today. And just to remind you, the goal was to tell the difference between a square wave and a sawtooth wave using this new tool, logistic regression. So we're not going to go in telling the computer anything in particular about triangle waves or sawtooth waves other than a bunch of labeled examples. And from that, it's going to learn something, what it needs to know to tell them apart. So we're going to start with square waves and sawtooth waves that are at the same frequency but arbitrary amplitudes and phases. So just to remind you what they look like and sound like, let's say that, okay, so I'll start off like this. So in blue we're seeing a sawtooth wave, and then the orange is a square wave. So let me listen to the sawtooth wave here. Alright, now there's something a little bit off about this. Actually, it'll be probably even worse if I go up in frequency. Let me go up to 80 Hertz here. So one octave up. Okay, so that doesn't sound very good. And the reason is because, so if I look at the Fourier transform of the sawtooth wave, I see this kind of strange pattern here. And, you know, I'm supposed to, if I remember the sawtooth wave, it's supposed to go down like in the harmonic series. But I see these other frequencies here in the middle. And what those are aliased frequencies that are higher. We've actually gone to a lower sample rate here of 8,000 because when we start to do machine learning, we're going to need a lot of parameters. And so if we can make our data have fewer samples, we'll need fewer parameters. So in machine learning, you often see either 8,000 samples per second or 16,000 when doing audio, because our ordinary rates of 2250 or 44,100 is just too many samples. And so we try to get away with fewer. But when we do that, we end up aliasing here, and it sounds like crap because we don't have enough. We don't have the sample rate to capture the frequency of the harmonics there. So what I have to do is upsample first by some factor. So say maybe a factor of 10, and then apply low-pass filter. So filter out the higher frequencies before downsampling so that we don't alias. So I talked about this in class before. And so anyway, this is what it ends up looking like in the waveform. And so the sawtooth wave and the square wave are kind of similar, but you know they have a little more wiggles in them because we don't have all the high frequencies we need to jump perfectly up, but that's okay. It looks much better in the frequency domain. We see we really damp down the aliasing quite a bit. And now I don't hear those weird like low frequency things. Okay, so that's kind of, just to remind you that the sawtooth wave is supposed to kind of approximate something like a bowed violin. Okay. Anyway, so we look at the sawtooth wave, we look at the square wave, and we see that, okay, sawtooth wave and the square wave have similar patterns. The sawtooth wave only has the odd harmonics, but the square wave has all of the harmonics. So that's one thing to remember about them. All right, so then, you know, in class we talked about how you can make a data set, a torch data set, out of this. And and actually, let me tweak this a little bit. So, oh no, that's okay. I guess I'll keep it as it is. Yeah. So what I was going to do here is say, okay, if this is, so I'll say y is equal to 0, but if this index is odd, or yeah, I guess I'll just say y is equal to index mod 2. So the label that this thing gets is going to be 0 if it's an even index, and 1 if it's an odd index. So if it's a 0, then I want to generate a square wave. So I'll say x is equal to, so we go up and get my method here. So x is equal to get square, and so I need a random amplitude and also need a random phase. So I'll say, okay, my amplitude, I'll just make mp.random.rand, maybe I'll say rand n, so possibly negative number actually. So that's it. So just one random number. And then my phase is going to be some uniformly random number between 0 and 2 pi. So rand gives me a random number between 0 and 1. Rand n gives me a number distributed according to the Gaussian centered at 0. Okay, so I've got my amplitude, I've got my phase. My frequency for now, I'll just, okay, so technically I'm going to choose a random frequency as well. And it's supposed to be between note number p min and p max. So I'll say frequency is 440 times 2 raised to the, so I'll make a random choice here, mp.random.rand int between P min and P max. So that's the note number. 2 raised to that note number over 12. That is the frequency that we have. And we're going to use the sample rate that was stored as an instance variable in this class. And we're going to use the number of samples like that. Okay, so if y is 0, we do that. Otherwise, we do a sawtooth wave. And we should actually convert these to torch arrays. So I'll say y is equal to torch dot from numpy, and I'll make sure these are 32-bit floats. So I'll say np.array y dtype equals np.float32, and I'll do the same thing for x. Okay, so I'm going to copy these over as 32-bit floats from numpy to torch, because I'm going to use torch to do the training here. Okay, so that's all I should need for my dataset class. Now I'll make a dataset with 2,000 samples. I'll make my node number range just be 0 to 0, so all the notes are going to be the same to begin with. And now I'm going to make a perceptron with the right dimension. Okay, so there's 1,000 audio samples. So every one of these arrays X that's returned has 1,000 samples. So the perceptron actually has 1,000 linear coefficients, and then it has that one bias. So technically it has 1,001 coefficients. So to set that up, I say perceptron equals nn dot linear. So 1,000 inputs, 1 output. That is then fed to the logistic function, right? Okay, so we got that, and now we've got the training loop here. So we're going to shuffle through in mini batches for each epoch here. I also want to accumulate the loss. So I'll get a loss for every example that passes through here. Let me go ahead and actually accumulate that. And I will also keep track of how many of these were correct predictions. So this y estimate gives me an estimate if this is actually the input to the logistic function, because it's just what comes out of the perceptron. I haven't put it through the logistic function yet. So if it's negative, then the estimate's going to end up being 0. If it's positive, the estimate's going to end up being 1. So I'll say, okay, the total number that I got correct, it's going to be equal to the sum of what it's supposed to be. So y, and maybe I'll say absolute value of y minus torch.sine y est. Okay, so if y is negative, this is going to be a -1. If y is positive, it's going to be a +1. I should better be a bit careful there, because what I should say is I should actually say it should be the sine plus 1, because okay, sine is going to give me a -1. If it's negative, it's going to give me a +1 if it's positive. So actually what I'm going to do is this will change it so that it gives me a 1 if estimate was 1, or 0 otherwise. Okay, so now I can compare it directly to, oops, I always use the numpy functions, I always sneak them in there. Now I can actually compare this directly to what the label is. Okay, so that's my total correct. I want to accumulate that. And then at the end of this epoch, I can record how many it got correct over the total number of data there were. And ideally that number would be 1 if it's working well. And then I'll just add that to an array, and I'll plot both these arrays. So let's see if I got that to work, or if I made a mistake somewhere. No, it looks like it's actually going through. Oh, abs takes 2 positional arg. Oh, sorry, I meant to write y estimate minus y. Okay. So if they're the same, this is going to be 0. If they're different, they're going to be, okay. So that should be good there. All right, so it's going through and it's training. It might actually be nice if I print out which epoch I'm in. So maybe I'll say print epoch blah loss equals, the loss, and then the accuracy equals the accuracy, just to see what kind of progress I'm making. So it's still going here. So I'll say epoch, loss, and then accuracy is last element. Okay, let me interrupt this and start it again so I can actually see a little bit more about what's happening. Okay, so here we go. So accuracy starts off at 0.5, so that's random guessing, right? It's like flipping a coin. So if I get half of them right, and it's supposed to be 1 or 0, that's random. And it doesn't really seem like it's making a whole lot of progress here, right? So did I do something wrong? Should I try to adjust the learning rate? And as we saw, there's nothing you can do, because this data is not linearly separable. So to see why these are not linearly separable, it's actually helpful to switch to a different coordinate system. But let's just quickly review the coordinate system that these are currently in. So if I were to, for example, grab out the first data element here, we know that's going to be a square wave because we made the even indices be square waves. So if I were to plot this, I see the following. I see 1,000 samples of the square wave. That's because I made this n 1,000 here. And so the input is an array with 1,000 elements. I'm just zooming in a little bit here, to show you. I'll just maybe slice out the first 100 and we see, yeah, okay, that's a square wave, right? So the input puts 1,000 dimensional vector, you could say, or an array with 1,000 elements. But this is actually not the most convenient coordinate system to see why it's impossible to linearly separate a square wave from a Sawtooth wave. So for that, I'm going to switch to a different coordinate system. And actually, I want to go back all the way to module 10, video 2, where I talked about the Sawtooth waves and square waves a little bit. So I'll review that again, but what I'm going to do is okay, so originally my 10,000 coordinates were just the audio samples, right? But I'm going to switch to a different coordinate system where the first 500 coordinates are the cosine components of the discrete Fourier transform frequencies, and the next 500 components are the sine components of the Fourier transform. So why is this coordinate system useful? Well, it's because it's what's known as an isometry over the original coordinate space. And what that means is it's not going to stretch the data in any weird way. Actually, it's just some kind of weird rotation in 10,000 dimensional space. But the upshot of this is, if I use the cosine component and the sine components as my coordinates instead of the original audio samples, here's something I can say. A set of audio clips is linearly separable in its audio coordinate space if and only if it is linearly separable in the cosine sine non-redundant DFT space. All right, so if I have 1,000 coordinates in the audio, there's going to be 500 non-redundant cosine components and 500 non-redundant sine components. So I will have the same number of dimensions. And I'm linearly separable in my original space if and only if I'm linearly separable in this space, if I'm using these arrays instead. And so what I'm going to do is focus on just one of the frequencies here. So if I go back to the module, I remember that the Sawtooth waves had every harmonic in them. So they had every integer multiple of the base frequency involved. Whereas the square wave only had every other harmonic involved, right? So that was one of the things that I talked about in that module, back module 10, video 2. So if you remember that, okay, here's what I'm going to do. I'm going to look at, I'm just going to focus on the frequency of the first harmonic. And I'm going to plot that, where I'm actually going to plot the cosine coordinate and the sine coordinate of that particular frequency on the x and y axis respectively. And so again, only the Sawtooth wave actually has a first harmonic, right? The square wave skips the first harmonic and goes directly to the second harmonic. And so what we see is as I vary the phase, as I phase shift each of these, these two dimensions together, the cosine component of the discrete Fourier transform and the sine component of the discrete Fourier transform at the first harmonic frequency, those are going to trace out a circle for the Sawtooth wave. But for the square wave, there is none of that harmonic. So it's going to be 0 the whole time. And so it's hard to know what to do with this particular dimension, because we know that we can't linearly separate something on the inside of a circle from something on the outside of a circle. I already showed you that. So it's like, okay, well, I mean, maybe I could just ignore these two dimensions because I can't linearly separate them, so maybe I should just throw them away. But I can't tell them apart by any of the other dimensions either, because I'm either going to be in a dimension where I have this kind of problem, so like, you know, the third harmonic only exists in the Sawtooth wave, but it doesn't exist. Or I'm going to be in a dimension where they both make a circle. And as I vary the amplitude, they'll trace out a disk. So either the dimensions seem like they're doing the same thing, right, because the harmonics exist in both, or I'm in a situation where I have like a point surrounded by a circle. And so this is not linearly separable. And personally, I just find this beautiful. You know, that's why I showed it before, and here it is again. So yeah, not linearly separable. Seems like a very simple problem, but we can't actually learn this with the logistic perceptron. But there's a simple tweak we can do to make this doable. And so you notice I sneaked in a little parameter to the constructor of the square sawtooth here, which is do FFT. So here's what we're going to do. If that FFT is true, we will transform the input so that it is replaced with the absolute value of the FFT of x. Okay? So we're going to change the input to be the FFT of x, but instead of using the sines and cosine components, we're actually going to replace them with their absolute value. So if you remember, what this does is this just replaces a particular Fourier coefficient with its magnitude. Okay, so we're going to throw away the phase. The phase is a nuisance parameter. Okay. One more thing I sneaked in here too. I'm going to add on a little bit of noise. That's just going to help a little bit with interpreting some of the parameters. So I'm just going to add a little bit of noise to each example. Okay. So let me run this code again. And now let's run the training again. Now a couple little things I changed. I made the learning rate smaller just so I could see, because it actually works extremely well in this case. And I want to slow it down so I can see it clicking into place. So actually I'm going to I'll go through 50 epochs. And actually I found a little mistake in my code that summed up the total correct, although it didn't affect the answer before. So I'm going to change that a little bit. Okay, so let's run the training now in this new data set where I'm going to return, actually I better change this. Let's change this to true so that I replace the input with the absolute value of its FFT. It says a little error here. Oh, I meant to say do FFT. So if self dot do FFT. There we go. Okay. Now let's train. And so we start off pretty random. But suddenly we jump up to very accurate. Okay, so I'm going to stop this video for a sec. I'll let it run. I'll show you the result. Okay, so actually I upped my learning rate here a little bit just so I could converge more quickly to some more informative parameters. And I also found a little bug in my code for adding noise. So the noise should be added before we do the FFT. Okay, anyway. So this basically completely slays. You know, it jumps right away to an accuracy of 100% basically and stays around there. And the loss just kind of stays at a very small number the whole time. But so this works very well. We can make the problem linearly separable when we pass over to the Fourier magnitudes. But yeah, let's actually look at the parameters that were learned in our model. So you remember the way that this works. If I go back to the other video, I showed that we have an input to the logistic function. And that input, if the input is positive, then the logistic function is above 0.5 and we say our estimate is 1. If that input is negative, then we estimate that the input is 0. And so the input to the logistic function is just some coefficient times the first element, the first index, plus some coefficient times the element of the second index, and so on and so forth. All the way up here, then plus a bias at the end. So I would like to know, what are the coefficients here? So what is it that I want to weight the first Fourier magnitude by, and what is it that I want to weight the second Fourier magnitude by, et cetera, so that I'm supposed to get a 0 for a square wave and a 1 for a sawtooth wave. So this whole number should be negative if I have a square wave, and it should be positive if I have a sawtooth wave. So let's go ahead and look at what it learned. So what I'll do is I'll plot an example square wave and an example sawtooth wave, so we can remember what they look like. So there's the Fourier there, and you can see just a tiny bit of noise. That's just to help me to see just to see the contrast here. So here's the coefficients we learned, and so I line them up here with an example square wave and an example sawtooth wave. So the square wave is supposed to be 0, so we're supposed to get a negative number. Now look what happens. We weight all of the coefficients where the square wave would have a harmonic, right? So those are all negative if I look down at them. We weight positive the ones that only the sawtooth has. And there's some random weights in the middle, but those don't really matter because most of the inputs are 0 there. So where the action is happening, we have positive weights for locations that only the sawtooth has, and we have negative weights for the ones that they both have in common. So when the sawtooth wave comes along, it's actually able to compensate for the negative stuff, and it's able to rise to a positive thing, whereas the square wave stays negative. Hey, so we actually learned something pretty informative. We went in with no idea, right? All we did was just pass along the Fourier transforms. So that was the one thing we had to do to make this work. But we passed along the Fourier transforms, but we didn't tell the model anything else. The model just learned that, hey, if I kind of weight these coefficients that only the sawtooth has positive, and weight the rest negative, then I'll be able to do this. So it actually learned that only the sawtooth has these coefficients. Pretty cool. And actually, if you keep going, you can actually, this code is general enough. We can learn to separate more than that. Not perfectly, but actually pretty well. So if I change the frequencies as well, I'll be able to separate square wave from sawtooth. Not as perfectly, but it's almost linearly separable. All right, so that's cool. But next I want to talk about what happens when what we have is not linearly separable, but we still want to do something. All right, so there we go.